Hello, welcome to today's webinar, Tolerancing with QC Software for Consistency. Presenting today is Mark Gunlock, a Solution Architect at X-Rite Pantone. I'm Robert Grotans, the Global Technical Marketing Manager, and I'll be moderating today's webinar. Before I turn it over to Mark, if you at any time during this webinar you have any questions, we do have a questions form on this page. Feel free to submit your questions. We'll also leave you some time at the end of this webinar to submit your questions. We will review your questions and we'll try to get back to you as soon as possible with answers to those questions. So with that, I'll turn it over to Mark to get things started.
Great, thanks, Robert. So let's just do that. Let's get into tolerancing with QC software for consistency. So color tolerancing can be done in a number of different ways. The big key is that we get visual agreement. So are we actually seeing in our software the same things that we're seeing visually with a physical observer? So why not just use visual standards and such to be able to do this evaluation? Well, check this out. In this case, is the A and the B, are they the same color? Do they look the same? A lot of people would say they're very different. Well, in fact, to connect these, you can kind of see how they're the same, but it's really tough. Let's mask that out. And here we can see they're actually exactly the same. But because of the surroundings, our eyes are fooled. Come back there, you can even see it it's hard to see if they look the same. There's a number of other factors, such as retinal fatigue, background effects, which is kind of what we're seeing here, poor memory color, our inability to memorize a color, physical deficiencies that our eyes just don't quite work well to differentiate colors. The lighting conditions, whether you're under fluorescent lighting or incandescent lighting, daylight, our age. As we get older, we're less able to tell colors very well, and so on. There's a number of others beyond this list that will impact your ability to judge color with physical standards and using your own eyes. So ultimately, though, it does come down to that visual guides are your ultimate method, okay? When we make decisions, we make purchases, if products look faded, if the colors don't look quite right, it can impact our desirability to buy that product. So there are a number of types of things we can use as physical targets for judging colors. Some of these range from, in production, we might use sample or print like drawdowns, or examples like this here you see on the left here. This is sometimes called a light standard dark or an LSD card. It has a sample there of a light tolerance and a dark tolerance range compared to the target we're trying to match directly, okay? Other examples, like on the right here, is a Munsell color tolerance set, which not only includes the light and dark ranges, but also includes ranges going off into the direction of red, towards green, towards yellow, and towards blue. These can be used as visual guides to compare your production to. However, they do have some shortcomings. They do require that they're produced in highly controlled environments. They have to be very, the reproduction of these have to be very, very precise. Otherwise, they don't serve any value at all if they vary quite a bit. You have to be under the right viewing conditions. You have to have a good viewing booth with the proper lighting conditions in there. You can't just use it under any kind of lighting. It's, of course, subjective. My judgment of a comparison visually may be a bit different than yours. And of course, these are also impacted by fading from exposure to light, soiling from dirty hands, and of course, scuffing, scratching, and just general wear. And most importantly is they don't provide a quantitative reporting. They don't give you a number for how far off things are. It's just simply a judgment call. So we need numbers, okay? So there is a thing called a color space that we utilize for determining differences in colors. We define colors within a color space. We can define distance between colors in this color space. So kind of like longitude, latitude, and altitude will describe where you are on the planet Earth. This color space uses 3 numbers to describe where you are within this range of colors. So the most intuitive model is something called LCH. And the L is describing how light or dark the color is. That's that axis right up the middle here. Okay, so is it a high value of moving towards white? Is it a low value moving towards black? And then the chroma is, well, how dull or vivid it is. So towards the center here, this is just all grays. As we move out from the center, we get to be more vivid in color. And then the hue angle, well, that's just going around the color wheel. Okay, 360 degrees around the color wheel will represent all the colors. Okay, so that's one way to look at color, and it will come into some methods we're going to tolerance later. Another way is just still in the exact same color space, but just describing a different way to move within that color space is something often referred to as lab, or L star, A star, B star. And the same L is there, light to dark, but now we have 2 different axes. Now, the A axis and the B axis. So the A axis, if you're in the negative direction, you're greenish values. If you're in the positive direction, you're in reddish values. And then along the blue axis, when you're in a negative value, the B axis is going to be a blue, okay? And then a positive B is going to be yellowish, okay? So that way we can describe where you are in relation to those axes to describe a specific color in that color space. And if you have an A and B value of 0, 0, that means you're right on the L axis, or you're neutral. So now that we can describe color with these numbers, and we can note exactly where it is in the space, we need to be able to way to describe differences in colors. Okay, so how far apart are these colors? And this is referred to as a delta E. So we start out with plotting where is that color in color space. That's our standard. And then the delta E describes how far in any direction are you allowed to vary in that color. What's acceptable in the distance from that standard, and that would be our tolerance. So there's a couple different kinds of tolerancing methods. So there's the unweighted color difference. In this case, we are allowing for equal weighting in all directions. Okay, so in any direction is equally important to us here. Now, this is the original delta E method that we've been using for years to find differences in color, sometimes referred to as delta EAB or delta E76. Very long time we've been using this in the press room, especially for CMYK inks and process measurements. However, it doesn't correlate very well with perceived differences in color. In other words, in some cases, you may look at something and it looks like there's a big difference in color, but the numeric values tell us it's a small difference, or vice versa. So that doesn't work out very well for tolerancing for color quality. So to compensate for that, there are weighted color difference methods. And in these, the hue, the chroma, and the lightness are weighted differently to improve the correlation to the way we see color difference. So when it says there's a big difference in color, we see it as a big difference in color. The first one that was used widely was called delta E CMC. It's still used somewhat, but it was used for years for the spot colors. More recently, delta E 2000 has become pretty much the standard in all of the ISO print standards and across a lot of brand quality requirements. And it's used for spot inks and CMYK inks. So rather than having Delta E 2000, or sorry, Delta E CMC used for spot color inks and Delta E 76 used for CMYK. Everything is moving to Delta E 2000. Makes it a lot simpler. Now, these two weighted methods work like this. First of all, they're weighted based on their location in color space, okay? So, and the hue is prioritized, okay? So we create these ellipsoids here, okay? Hue is much more important than the chroma or the lightness, okay? So we allow the color to move more in chroma and lightness, but we don't allow it to move as much in hue. The duller colors have tighter tolerance ellipsoids, as you see towards the center of this model. They're much smaller ellipsoids as we get closer to gray and the pastels. And the more vibrant colors, as we get out towards the edge here, they have much larger ellipsoids, allowing for a lot more movement in that color. There's also a concept of weighting factor specification. These tolerance methods include weighting factors that can be set by the user to change the shapes of these ellipsoids to compensate for the differences in our perceived color difference. With the CMC, the ratio is lightness to chroma, and since the eye will generally accept a larger difference in lightness, L, than in chroma, C, the common ratio is L to C, or 2:1. This 2:1 ratio will allow for twice as much difference in the lightness as in the chroma. Now, in some cases, you'll find a ratio of 1:1 that's also used, but very commonly 2:1. So those are the two you're going to see out there the most. It's 2:1 and sometimes 1:1. Now, with Delta E 2000, the math was actually built to compensate for that ratio right from the start. So the 1:1:1 weighting factor is generally not modified. It's generally left at that default. There's a couple other tolerance methods out there that are used for special applications. Like for those of you that are doing G7 work for gray balance, there's two special ones there. There's a Delta L that looks at the difference in lightness without regard to the color. And then there's a Delta CH that looks for the difference in the color without regard to the lightness. And then for flexographic ink validation, due to the wide variety of printing inks and the substrates we're printing on, and the various properties that the inks have to have for different kinds of applications, whether it's for food product or scuff resistance or fade resistance, real big concern there is trying to match that hue angle of the ink color. So in special cases, the ISO specification speaks about matching a target ink color hue under a defined delta H sub AB. So we're just looking at the hue angle of that ink and trying to match it to some standard hue angle. So what methods should you use? Got so many out there, okay? So what it really boils down to is this. First of all, whatever it is, you always have to communicate both the tolerancing method and the weighting factor, okay? If you're not communicating all that, you're going to get some disconnects in how you're communicating color, and you may get pass and fail that are different than what your print buyer is looking at, or vice versa, okay? So you need to make sure that whatever it is, you notate that in your documentation and communicate that to all parties concerned, okay? Now, unless you're otherwise directed by your print buyer, make sure you follow the standards of Delta E 2000 111, all right? That's where everybody is moving. That's where, again, all the ISO standards are there, and most customers, most print buyers are looking to move to that direction. So that's where you should go if there's nothing else has been defined there. If the customer does request another method and weighting factor, make sure everybody's using the same. Now, what tolerances should you use? Not just the method, but what should I be looking for? Delta E at 1? Will that be ideal, or 2? we have to be realistic. This is an agreement between the buyer and the print supplier. This is based on process capability. What can we expect a process to be able to hold? Some printing processes are more consistent than others. So as an example, many offset printing suppliers use tolerances like this, and this is very, very common. So they'll have Delta 2000, 1 to 1 to 1, as we described earlier. The CMY inks will have a tolerance of up to 3.5 delta E. The black is a little bit more on there, it's up to 5. And then spot inks are going to be a little bit tighter, closer to under 2 delta E. For some other print conditions, they may require a little bit larger tolerances. So you may, in fact, start out with something close to what those offset tolerances are. And those are used across other different kinds of print conditions. But you may find that the type of printing you're doing, maybe it has to do with the type of substrate you're printing on, or the nature of the printing press, or other variables go into that printing process that cause for more variability in that production. And if that's the case, oftentimes what will be done is testing will be done where you do like statistical assessment on production using models like X-bar R charts. A lot of statisticians know about this kind of stuff. But you're trying to find out what kind of control can you hold on that press, and you look at the data that's measured, and then you evaluate it and you look at if there are things that are out of control at certain points in this graph. You go back and look how that production was done, and you check the variables out and try to figure out the root causes. And is it something you can control, in which case we don't change the tolerance? Or is it something that's just the nature of the process and you can't control that, in which case you may have to widen the tolerance to accommodate that behavior of a well-controlled press, just has that natural tendency to vary a certain amount. So you may need to do some of that work to figure out your best tolerance target values. So let's take a look. So what would, when things go wrong? So if I pass on my tolerance, but the customer still rejects it, what can I do? Well, first of all, you need to make sure that you're all looking at everything the same way. You have the same parameters when you're assessing. So the lighting and illuminance specifications in the print industry are all specified to D50. If you've got people viewing physical standards under other lighting conditions, or if their instruments are set up for something other than D50, you're not going to have matching results. You need to make sure that software is configured with the same settings across all your software and hardware. That's one of the most common things we here at X-Rite hear about is when people complain about mismatched values between software or devices. As we get into it and look at it, it turns out someone's got something set to a different color setting, like D50 versus D65, or things like that. We want to make sure that we're using the same type of instrument geometry. A handheld X-Acto has very different internal geometry than a handheld benchtop or sphere device. And the numbers between those types of devices aren't compatible with each other. So an X-Acto is a 0.45 instrument, and a benchtop or sphere, those numbers don't correlate with each other, okay? Also, keep in mind that substrates like non-opaque materials, whether it's papers or films, they'll allow backing material to show through. So if I measure on a white backer and you measure on a black one, we're going to get different numbers because of the backer showing through that material. We need to make sure we're measuring under the same conditions on the same type of material. And then, are the tolerances, as I mentioned in a previous slide, are they even realistic for the type of printing we're doing? You know, some processes are going to be more widely variable. So we need to perhaps adjust our tolerances for that. So that is all I've got for today. And I thank you for your attention. I'm going to turn it over to Robert.
Great. Thank you, Mark. So yeah, once again, if you do have any questions for us, please feel free to submit those using the questions form. We definitely would like to hear them and see them. We will do our best to follow up with you as soon as possible on any questions that we do receive. So we'll leave that up for a little bit. But for today, we will end here. And again, thank you all for watching. Have a good rest of your day.